All right, let's go ahead and move on to 3.4, influential points and outliers. So the first thing here actually I would talk about before we move into this section is outliers. We had talked about outliers before in univariate data. So remember, univariate data has one variable. Bivariate data, which is what this whole chapter is about, bivariate data has two variables. So in univariate data, we said anything that's 1.5 interquartile ranges below the first quartile, or 1.5 interquartile ranges above the third quartile was considered an outlier. That's not really something that we can calculate with bivariate data, and unfortunately there really isn't a good way to actually calculate, like use math to confirm that something is an outlier with bivariate data. But we can look and see how far apart data is and determine if something likely is an outlier based on how it influences our graph or our line of best fit, really. So in bivariate data, in general, we say an outlier is one that's far away from most of the data in the y direction, so up or down. Think of it this way. In this picture here, with the original, my line of best fit would be something like, well, maybe a little higher than that. Maybe like, kind of like that. And then with this outlier that they have in part B, it's like way up here. You imagine that I just kind of ignore that outlier for a second, looking at the original line of best fit, the residual for that outlier would be very large residual. So when I find the line of best fit for that outlier, my line, you can actually see it here, the line actually has to move up a little bit, and the residual is still pretty big, even with that line moved up. So if you have a very large residual for a specific point in your data, that point is probably an outlier. Notice how the residuals for all of my other points on here are much smaller than that one. Even this one here, which is probably the next biggest one, is still not nearly as large as this one up here. Okay, the next thing is an influential point. An influential point is a point that lies far from the data in the x direction, so either left or right. Okay, and they don't give an example of a point that's just an influential point here. They have over here where it says that this point is an influential point and an outlier, but an influential point is one that it basically is just left or right of the data. So if I copy this original, I can draw the line of best fit again, or sketch it, I guess, it's not perfect. And then any point that's like way off to the right or to the left of that data, like maybe this point right here, would be considered an influential point. But you see that point that I just drew, that influential point there, lies pretty much right on the line that I drew. In fact, it kind of guides that line in that direction. So it is possible that an influential point might not affect the line of best fit at all. But as soon as I take that influential point and I move it up or down to make it an influential point and an outlier, that's definitely going to have an effect on our line of best fit. Because now our line of best fit is going to have to do this kind of thing so that it's closer to that. And now our residual is actually not very big because it had to shift. So in general, an influential point might not change your line of best fit very much, but it does lie far away from the graph in the left or right direction. So just remember, right or left, it's an influential point. Up or down, it's an outlier. If it's both, then it's both. It is possible for a point to be both an influential point and an outlier, like it is here in graph C. It's far to the right and it's far down. So they have some pictures here that show you the lines of best fits and how they are affected. With the first one, you can see your slope goes from 0.8 to about 0.6. That's not much of a change, it's a little bit of a shift. Your y-intercept, though, goes from 0.3 to 1.8. That's actually a pretty significant shift upwards. So that's how an outlier might affect it. We already talked about how an influential point might not affect a graph at all, but if something is an influential point and an outlier, it's going to have a huge effect. So looking at this one, you can see this point over here is an influential point and an outlier. The slope goes from 0.1 to about 0.8. Huge shift. You can see that in the graph. It goes from pretty steep to very shallow. The y-intercept goes from 0.27, so 0.3 to 2.6. Huge shift in the y-intercept also. So an outlier can have a big effect on a graph and on a line of best fit, but if something is both an influential point and an outlier, it has a very big effect on our line of best fit. And then of course on the next one, they put it all together. They give you both of those points, the outlier and the one that is an outlier and an influential point, and our line of best fit is just thrown way off because of that. So you imagine you're trying to make predictions about things in this data set, and maybe you're trying to make a prediction for when x is this value here, and you get this number, which does not follow the general pattern of data at all. So the problem with these outliers and these influential points that are also outliers is that it throws off our line of best fit so much that our predictions are no longer reliable. So sometimes it can make sense. Ooh, what's going on? Hold on. Make it big. There we go. Sometimes it can make sense to actually just remove an outlier. Or if something is both an influential point and an outlier, we might remove that also. So the problem with removing things, though, is you're literally taking a piece of data and saying that it's not important. So you really have to look at the context of your problem and the context of the data point that you're looking at and ask yourself, is it really okay to just get rid of this data? Is it really okay for me to ignore this and to exclude maybe this whole person and say that they're not important? In general, it's not usually a good thing to do. So you have to have a very good reason to get rid of data points. And one of those good reasons actually might even be that there's an error in your data. Maybe somebody was did a biased experiment. Maybe the data point is completely invalid. Maybe you're looking at test scores, and one of your scores is somebody who cheated, or one of your scores is from somebody who fell asleep and didn't do anything. Those would definitely be outliers, and you would want to retest those people rather than just throw them out. So all things to consider. And I believe actually in the quiz that you have for this section, they asked like what types of situations would make this outlier happen? And that's where you would talk about things like, cheating on an exam or falling asleep, or maybe there was a fire drill and things just went all crazy. So these are things that statisticians do actually have to think about. So on the next page, we have an examples from 3.4.3. This is not a graded assignment here, so I figured I'd go through some of these with you. They say to create a scatter plot for this following data set. And then it gives you some options to set its window at. We're going to find its correlation coefficient, its regression coefficient, which means it's the slope. Remember, regression coefficient is the slope of the least squares regression line. And then we're going to look at the scatter plot and a bunch of other stuff. Let's just go ahead and get into it. All right, so I went ahead and put my data into my list here. All of my X values are in L1, all of my Y values are in L2, and they're all left and right. We have our points connected, nothing's off at all. And then I went into my window and I set my window the way that they suggested with the X-min, X-max, and so on. And I went into my stat plot, turned that on, make sure my L1 and L2 are highlighted, and I'm using a scatter plot. Now when I hit graph, I can see my scatter plot looks like this. And I would probably want to sketch that on my assignment to show that I did that correctly. The next thing it has to do is to find the correlation coefficient of this data. So again, we get a correlation coefficient when we calculate our linear regression, our least squares regression line. So to do that, I'm going to go ahead and hit Stat, move over to Calculate, and choose option 8, linreg A plus BX. Make sure I have list 1 and list 2 in there, and I'll go ahead and store my line in there also by going vars, y vars, function, y1, so that it stores it into my y equals so that I can graph the line of best fit too if I need to and make predictions, because there's a lot of things on this page that I might need that for. And I'll hit calculate. And on my screen, I have something missing. You know, from 3.3, I should have an r squared and an r down here. If you ever have that happen on your calculator, it's because of your settings. So to fix this, I'm going to go into mode, right here, mode. And I'm going to go, I think it's all the way at the bottom. All the way at the bottom. Stat diagnostics. See how my stat diagnostics are off? This is stat class. So we definitely want our stat diagnostics to be on. So I'll scroll over and click enter to turn that on. And then I'll get out of that screen by hitting second mode to quit. Now let's try that again. Stat, calculate, option 8. We already stored that, so I'll just hit calculate. There we go. Now I can see my correlation coefficient is, for part B, R is approximately 0.715, I would round it to. Okay, next thing it says, I'll write that down, I guess. R is approximately 0.715. Next thing it asks is, what is the value of the regression coefficient from the least squares regression equation? Remember, the regression coefficient is the slope, and the slope of this line, y equals a plus bx, the slope is b, and b is 0.83674. So I'll say b is approximately 0.837. Or B1, I should say, is approximately 0.837. Okay? And it doesn't say to interpret that, so I'll just leave it at that. Next part, D, it says the point in the upper right-hand corner of your scatter plot, 2, 4.05. Let's see what they're talking about. Oh, there's that nice least squares regression line. So I'm guessing they're talking about this line right here. Where's my, you can't see my little, there it is. This line here, this point here, I'm guessing is 2, 4.5. I can verify that by hitting the trace button, which will highlight specific points, and then I can move left and right. Yep, that point right there is 2, 4.5. So that's what they're referring to. Complete the following table, which shows you what happens as this point is moved straight down. What do you notice about the correlation coefficient and the regression coefficient? Note that you can fill in the first row of this table from your answers to B and C above. Remember to efficiently recompute R and B each time after you go back and change a list to your y value. So there's quite a bit of work here. So the first thing I want us to do is copy down R and B that we just wrote. R was 0.7-ish. B was 0.8-ish. So now they want us to go into our list and change that 2, 4.5, this one, to 2, 3. See how I changed that? It's not 4.5, now it is 3. And when I do that, I now need to recalculate my correlation coefficient and my slope. And to do that, I'm just gonna go stat, calculate, option 8 again. And I'm just gonna enter, calculate it, so I can get those numbers real quick. R is now 0.657 and B is now 0.667. That's if I round it, 0.7 and 0.7. Now let's change it again. Now they want us to change that 3 to a 2. So I go stat, edit, change the 2, 3 to 2, 2. Enter. And then calculate your regression again. Enter. Now R is 0.6 and B is 0.6. And then one more time, stat, edit, change the 3 to a 1, enter, stat, calculate, option 8, enter. Now R is 0.4 and B is 0.4. And remember, this makes sense because in, which section was it? 3.3, the regression coefficient and the slope of your line are directly related using the sample standard deviations of your variables. So as one is affected, the other will be directly affected also. So we filled all that in. What do you notice about the correlation coefficient and the regression coefficient? So I would say we note as y decreases, r and b also both decrease, I would say proportionally even. Next thing they say to do, complete the following table, which shows what happens as a point 2, 4.5 is moved back and forth. So we're gonna go back to our, oops, come on. We're gonna go back to our lists again. I'll change that back to a 4.5 like it was before. And now we're gonna go ahead and play with this 2 here. So we can start with what it was originally, 0.7 and 0.8 when we rounded. And now let's mess with that x variable. So we're moving it left and right. So if we move to the left to 1, and then recalculate our linear regression. Now r is 0.6 and b is 0.8. Now let's change that x value to -1. Stat, edit. Second one down, make it -1. Recalculate your linear regression. Now r is 0.3 and b is 0.4. And one more time, stat, edit, change that -1 to a -2. Stat, calculate, option 8. Now it's 0.1 and 0.2. So we notice at first our slope wasn't affected at all, and it was just our slope that was affected slightly. And then as we continue to move to the left, our slope and our correlation coefficient ended up both being affected quite a bit actually. Okay, so remember something that is far up and far down. So this here we were creating outliers, and on this one we were creating an influential point, which eventually became both an influential point and an outlier. Which is why when we first moved it to the left, it didn't really affect it much at all. And then when we moved left a second time, it became not just an influential point, but an outlier also, which is why it had a much bigger